Okay, everyone. Let's begin our second linked list lecture. So, linked lists. Let's remember what we did before. So, we talked about a singly linked list. Well, hang on. I'm not sure if it needed to be fixed. Let's check. CMSC 341 spring 21. Yeah, it's right here. I guess I haven't uploaded the linked list code yet. The GitHub link is on the course page. I'll check. I haven't checked. Maybe it's not. Let's see. Is it? Probably. I guess it's not. I'll send it out as an announcement. Okay, maybe the one in the syllabus is bad. I'll check that. Let's see here. It might be a capitalization issue or something. There we go. Fixed. Okay. Okay. So, we built a singly linked list. So we did the CRUD operations. We did create. I always forget what R is. I think update and destroy. Is it retrieve? Basically, read. So, sure. Incidentally, I'm not going to be testing you on the acronym CRUD or anything. But basically, we did insertion, deletion of a node, insertion of a node, both at the, well, we did it a number of ways. We did it at a position, deletion of a node with a value. So, and then what else? We did search, and I don't know if we handled destructors yet. I think we haven't actually done destroy. So I was going to show you the two ways that we can, basically I think there's really two ways that you can do a destructor for a structure like this. Oh no, we did a destructor. I did the destructor in the kind of 341-ish way, where you delete the head and then advance. So we're about to look at the code again. So let's remind ourselves what we did, and yeah. So there's another way to do a destructor, which I actually vastly prefer. But the only problem is that you can't always use these on projects. And the problem with them is that the reason why you can't use them on projects a lot of the time is that you won't be allowed to modify the node struct class. So that's the real issue, is that I actually vastly prefer the second method, but a lot of times you're not allowed to use it. So it's kind of unfortunate, but I'd like you to know about it just in case you get the freedom to design your own node class in the future, which would be great. because then this method, I don't know if you'll like this method more or not, but why don't I just show it to you and then you can decide. Yeah, so let's look at, so I think we've done the destructor here. Yes. So here's another way of doing destructor. So let's go back to our linked list .h, where we are already. So here's a cute way of doing it. So say you want to delete a linked list node, right? So actually, let's just draw it out, and I'll show you what's going to happen. So let's make myself a little linked list, and I guess we want that feels better, doesn't it? With the rounded edges. I like that better with the rounded edges. So let's make ourselves a linked list. Here we go. And then let's do some kind of spacing issue. Whoa. Oops. There we go. And then let's put some arrows in. Then Control-Shift-F, stroke, arrow. Really, I should have done this before I made the structure. There we go. That's better. Okay. So here's a linked list, right? We have our head node, we have our pointers to next, we have some data inside these blobs, right? So this is a linked list. So imagine, instead of deleting the head and then updating and deleting and updating and deleting and updating and deleting, you told each node when it got its delete command, or really the destructor, right? When it got its destructor call, or I'm calling it a delete command, then what it does is it checks if the next node exists, and then it sends the delete command to its next pointer, right? So what happens is that when you send the delete command to, say, the head node, what it's going to do is the first thing it does is it sends the delete command to this node, then it sends the delete command to this node, then it sends the delete command to this node, this node, this node, this node, and finally this node sends the delete command to this node. Now this node sees that it has a null pointer sitting at the end, right? So what it does is it will just return, because it's like, okay, I don't have anything here, so I'm just going to not, there's nothing to delete here because I don't have a next. So I'm going to return out of my destructor. And then what this thing does is this thing finishes its delete command on this guy. So then this guy disappears, and then this guy will disappear because then this guy will finish his delete command on him. So gone. And then this one will have its delete command finished. And then this one will have its delete command finished, and it'll propagate back like this, all the way back, all the way back. And then finally, the first delete command that you issue is actually in the destructor of your main class, so in the linked list class. So this is the linked list destructor that finally destroys this last node. So, so basically, the first destructor that we did, this was the first method that we used, right? Destroy this way, right? And then the second method that I'm describing now, this is my new method, right? You trace down you trace down to the end, but then the deletion actually happens backwards, which is kind of cool. So let's see what happens if we do this. So basically, all you have to do here, and this makes the destructor really simple, is you say if pNext delete pNext. That's it. We're done. And then that's all we have to do, because it checks if it has a next and then it deletes it. Here it might be saying the if statement is unnecessary, deleting null pointers has no effect. So actually, as long as I like doing this just because it feels safe, but okay, you can even just do this. Okay, so this is totally legal, right? And this will delete everything in your. As soon as your data structure deallocates, this will delete everything except for the head node. And then, instead of calling clear, here's our destructor, and that's it. You know. And that's it. So that's the method that I prefer. Because you see that what it does is this linked list, it only ever actually deletes one node. But as soon as it deletes a node, then the rest of the linked list will be deleted. So, yep, that is how it works. So that's an interesting. I think it's a good way to do a destructor. The only thing you might have to do is when you're doing your remove method, instead of just deleting old head, you're going to have to set old head.pnext equals to null pointer. And here you're going to have to set pdelete pnext equals to null pointer. That way it forgets what's going on after it, so it doesn't delete it. So here this is the one modification you have to make. Now this won't have any effect. Or in the original case. But it will prevent you from accidentally deleting the rest of your linked list. So, okay, I think that's all I really want to say about this. I think this is kind of a anyway. So I think this is kind of a cute little way to do a destructor. It definitely simplifies matters quite a bit, right? You know, and destructors can often be really kind of hair-pulling, because the problem with destructors is that that's where you're going to get a lot of your seg faults, because you know, so you might have done something bad already, say in a copy constructor or in an insert method or something, but it's only going to actually come back to bite you when you get into the destructor, because that's when it's actually going to try to delete the data structure. And then whatever mistake you made in the other methods, so like in insert, in remove, whatever, that's when they're going to generally come back at you. So I think what I have to say about it is that whenever you do like a GDB on your code and it ends up that your destructor has an issue, the first thing you should do is you should look at your destructor. And then the second thing that you should do is you should look at everything else, because a lot of the time the problem is found outside of the destructor, and that's as simple as that, right? I mean, so okay, all right. So let's actually run this linked list code. So let's write some main code instead of just talking about it. So okay, let's see out, say, enter command. And so let's make up some commands. I've done way too much Python. So, okay, so basically, what are we going to do? If command is equal to insert, we'll do something. If command is equal to remove, we'll do something. I guess we can even do else if command is equal to display. Then, so let's make a linked list. There you go. And then what else are we going to do? I guess here we'll just say linked list, my linked list. So in general, you don't need to make these pointers. I've seen a lot of people make the linked list itself a pointer when you're doing testing. You don't have to do that, just in case you were thinking that for some reason you had to do that. So let's see. So we need to make an int data. So we're not going to test the insertion at position. Well, we can, I guess. Let's do it this way. So regular insert will insert at end. So, and then if we do insert at pause, then we can see in data, right? And now we need an int position. And then what else do we need? Here's our my linked list dot display. So there's a little cout method that I implemented. Cin what data, right? But this is what to remove. And then list dot remove data. Actually, we should always just display it, right? Because that'll help. And then instead of having a display command. And then here we'll do insert data position. Why doesn't it like this? Does it want the position? Yes. Something is wrong with my default arguments. So here we have position is equal to end. I think this might need to be in the class constructor here. Let's see if that fixes this. Yes, it does. Okay. And then, I think we should be good, right? Unless I've done something crazy. And of course, at the end, the destructor will run. So we'll find out what's happened. Okay, so let's see if this works. Don't you love live coding? Let's see what happens. Building, linking. Okay, let's insert 5. Let's insert 10. Ooh, infinite loop. Wonderful. So what happened? We have a 0 and so we have an infinite loop. What did I do? So so this one worked if pcurrent.pnext is not equal to null pointer. This is the problem. So what's going wrong here? So it seems like, oh, interesting. It's inserting Oh. Ah. You might. There we go. There we go. Let's. So there was nothing wrong with the insert command. That's why I was having a little trouble. I was like, I think that this looks fine to me. I really didn't understand. I'm sure all of you were screaming in your heads, but you didn't get a new command at the end. So it was just going to infinite loop, right? Because the command was always going to be insert. It was going to ask for data. I guess it just kind of, not sure how it blasted through that, but it did, and then it just kind of kept blasting through over and over and inserting 0, I suppose. So that was strange. Fair enough. Fair enough. Let's fix the display method. I think there's an end line in the display method that shouldn't be there. Maybe it's in the .h file. Where is this? Where is display? Here it is. Ah, here it is. Because I don't like how it's doing this. I want it to be okay. Let's try again. This time, maybe it'll work. So let's insert 5, insert 10, insert, I don't know. Let's insert at pause. Let's try to insert 2 at position 1. So hopefully we're going to see a 2 pop in between here and here. And it does. All right. Insert at position, maybe 0. Oh no, I'm sorry. Let's insert 3 at position 0. So remember that this is inserting at the head, right? Good. So now let's remove 2 and make sure it doesn't break. So this is definitely one of those possibilities that something could be broken. Wonderful. Didn't break. You know, it's always a bit of a crapshoot. Let's see. Let's insert 20, insert 30, insert 50, and then let's remove 30 again. Cool. So you see how a linked list is kind of working, right? And don't worry, guys. I will give you this code. I'll upload this to the GitHub after class, now that it's more or less complete. Okay? So, any questions about how this is working? Any questions about what the operations are? Any questions about anything? I think I've demonstrated a coded up linked list, right? You guys are kind of quiet today. You're all just experiencing the on the other hand, okay, let me see if I can, all right, cool. So, and now, remember, so this is the moment of truth, right? This is the moment of truth, because we're about to run QUIT. So that ran fine, but maybe it didn't run fine, right? Maybe it broke and we don't know. So I don't have my C line set up for anything, so let me just WinSCP into my GL server. No, I don't want to upgrade right now. I'll upgrade later. Or actually, maybe I'll just use Bitvice because I'm even lazier. So, oh crap, that's a lot of crap. Okay. All right, let's see. Okay. All right. Okay. Cancel. I think it has to be password KBDI. Okay, what's causing this trouble? Alright, I'm just gonna, never mind. What SCP it is. So, what the ass? I actually displayed my password. Complete. Okay, I'm getting access. Okay, now I'm confused. I'm actually getting access denied to GL. Oh, my username. Okay, there we go. I was so confused. Very confused. Okay, let's make a linked list project here. And then I'll just drag and drop the code. Because that's, unfortunately, this is the way I'm doing it right now, so because I don't have like SSH set up natively in CLine right now. Okay. All right, there we go. So let's Alright, so now let's G++ with a G option. Let's do linked list.cpp and main.cpp, and let's make the output file, I don't know, what should the output file be? Linked list. Okay, so now let's val grind this thing. Oh yeah, we have to do like insert 5, insert 10, insert 20, insert at position 3, 2, insert at position, say 100, insert it at position 100. Ooh, so that was a problem. So you see that we had a too far issue, which means that we're actually tracking down the linked list too far when our position is beyond the length of the linked list, which I thought we had dealt with. Oh. Okay, no, actually we're good. So, do you remember how everybody talked about exceptions? Well, here's the exception. It said, your insertion position is too far, your insertion position is too far, right? So I didn't catch this exception, right? So I threw it but didn't catch it. So I forgot that I'd inserted that in there. So let's actually do the catching of the exception. So let's emacs main.cpp. And now what we're going to do here is we're going to, so this is how you go through the process. You try, right? And try means inside of here, bad things are allowed to happen, right? So inside of this try block, exceptions are allowed to happen, and then you need to do a catch. And in this case, we're going to catch, I think I made it a range error, and so we're catching a range error, and then we can see out the range error, which I think usually has some kind of cout function. So let's try this and see if that. So this was actually not a val grind issue. This was a I forgot to catch the except. Whoa. Did they not overload the? Okay, it's dot what? Okay, it's gonna be range error dot. I thought that I misremembered. I thought that they'd overloaded the cout operator for this stuff, but I think we need to do that. So let's try to recompile. Good. So let's just run a linked list as usual. So let's insert 5, insert 10, insert 20, insert 30, insert 42, insert 1779, insert 21. Okay. So that's all inserting at the end, and now let's try to insert at position. Like say, we'll insert 3 at position 3. There we go. Insert at position, and let's insert 3 at position 1000. So you see here that we threw the error here, right? And so throw is a kind of return statement, but it's a much more powerful return statement. It's actually more like a go-to statement. Basically what it does is it forces this function to terminate and it returns immediately. And then what it does is it pops out of here and it goes back to the main, which of course doesn't have the try block in here. I should put the try block in there. So let's quit here. So here, you see that this was the function that got like force return, right? Now this is the function that threw the exception. And so wherever this is in your try code, this entire try block is going to end, right? So this try block ends, and then it goes to catch, and then it catches the range error. Now if it's a different error than a range error, it won't catch it. So basically this will only catch a range error. So if there's like a domain error, if there's some kind of pointer exception, if there's anything else other than a standard range error, it won't catch it here. So you can actually do other catches. You can say, well, you can have multiple catch blocks if you have multiple errors. So say you want to catch a domain error, and something different happens, right? Right. This is totally legal. You can do this too. But yeah, so in this case, we're only catching range errors because that's the only type of error that our program at least throws. Any other error, we're just allowing to crash our program. And so yeah, basically there we have try, which allows us to run a block of code that might throw an exception, right? So anything in here is allowed to throw a range error exception. And when it does, is it jumps to here, and that's what it does. Okay. So, yep. And if it's not a range error, then what it actually does is it forces main to return, which is why it crashes your program. So, okay. Let's run valgrind again. Let's see, insert 5, insert 10, insert 20, insert 30, insert 40. I don't know why I'm just inserting 10s, but it doesn't really matter what the data is. So remember what this does. It removes the first instance that it finds. So it actually removed this one. It didn't remove, so these last two got to stay. And now here, we get to quit. And so here we see some good news. 11 allocations, 11 frees, 74,000 bytes. So it seems like what happens is that the operating system allocates a huge amount of memory as well, which is why you get 74,000 bytes, freed. Each individual, let's look at each individual linked list node, right, that gets allocated. When you allocate a new linked list node, so all of these functions, they don't get allocated for new linked list nodes, right? So basically it's the same functions for everybody. At least the memory location of the functions are all the same. The only thing that gets allocated when you allocate a new linked list node are these two things. So you end up with a pointer pnext, which is, at least in 64-bit language, it's a 8-byte pointer. And then here is an integer, which is still 4 bytes. So each one of these linked list structures is 12 bytes total. Okay, so that's all, right? So when you see these like huge 74,000 stuff, the real issue is in use. 0 bytes and 0 blocks. All heap blocks were freed. No leaks are possible. So does this mean that our program runs completely without memory leaks? And the answer is no, because it's always possible that some code that didn't get executed will result in a memory leak, right? So you do have to make sure that when you write your tests, you write complete tests that test most of the edge cases, right? So if we wanted to write some test cases, we'd want to test, for instance, like if you insert and remove and insert and remove and insert and remove, just to make sure that the empty linked list processes don't screw up, and then you might want to try inserting a bunch of random positions, and basically if you just do a whole bunch of random stuff, but also you should think about what may cause an error and try to design a test that if that error will happen, that test will cause the error. So really, like a good test, this is more like philosophy than anything, but a good test always tries to determine what will cause an error and then try to get it to happen, right? If your code is right, then it won't happen, right? Then that case won't cause an error. But if there's a bug, hopefully you'll actually cause the error with the test. So causing an error with a test is a way better thing than causing an error just in if you quote-unquote shipped your program and then it failed, you wouldn't want that. So it's better to design a test that fails, that's finicky. If the test is finicky and it fails as soon as any of those errors happen, that's a good test. If the test doesn't always detect the error, then that's kind of a bad test, because you might say something like, oh, cout, pointer test passed, but then you'll get a segfault later on. So that's kind of the moral of the story. So that's basically it for coding up this linked list. So let's talk about, I'm not sure that I'm going to actually code up everything else, but let's talk about some other structures that you can make with linked lists. Here we are. Okay, so we've done the 2 destructors. We've done create, update, read, destroy, create, read, update, destroy, whatever. So there's 2 other data structures that I want to talk about, which are circular linked lists. And so let's talk about circularly linked lists first. And then there's also doubly linked lists, which I'll get into. So a circularly linked list is a linked list. Yes. Everything is the same, right? The data structure, the node for a circularly linked list is the same node as the regular linked list, right? So it's the same node, but there's one exception. This last node here, instead of being a pointer to null, let's see if I can draw this. Let's see how good I can do. Not very good. Okay. Oh, because I had the wrong thing clicked. That's not bad. That is not bad. Let's put an arrow on that. Or maybe. I think maybe I have to page it up. Is the arrow just underneath? Yeah, it is. I don't know why it's not putting, there we go. Alright, there we are. That's actually not bad. there's a little bit of a cusp point right here, but can't even see it here. So not bad, eh? So you're still going to keep track of a head node, you know, M head or P head or whatever you want to call it. But the problem is that the tail node, here's P tail, which probably isn't, you probably don't keep track of it. Right? You probably don't keep track of this node, but here's the thing. How can you tell? So this leads to an important question. How can you tell that you're at the end of this structure, right? So basically, you have a pointer at the very end that leads back to the head. So how can you tell, right? Because in the regular linked list, we check if pNext is equal to null pointer, right? But in this case, pNext is never going to be null pointer. That's right. So if pNext is equal to the M head, that's right. So yeah, basically what you do is you check that if some node pNext is equal to M head, you know, then you're back at the start. So don't keep going, right? So basically, if we're going to modify our linked list class, and maybe we'll just actually do it, because there's no reason not to. Let's actually do it. So let's make a circular class. Let's call it circular link. And basically what we're going to do, I think, is we're just going to copy and paste everything from here into circularlinked.h, and then we will copy paste everything from linkedList.cpp into circularlink.cpp, and then we should be good. No problem, except for all the problems. Oh yeah, we don't have a linked. We don't have a whatchamacallit. So, oh wait, yeah, let's just do it this way. So we actually probably can't use this destructor anymore. We might actually have to do a regular clear method. So actually, let's use a regular clear method. Circular link. Oh, you know what we never implemented? We never implemented a copy constructor. So that's something. And I think we have to include like IOStream. Okay. I think that should basically handle it. What else is the problem? Oh wait, position equals end. Okay, there we go. Okay, so I think we're good. I mean, I don't know if I'm actually going to compile this code because this code could just explode. Now that I've kind of copy-pasted, but let's think about the things that we have to modify. So we'll worry about the destructor next. So basically, so here we're going to have to, unfortunately for display, we're going to have to do something a little bit more annoying because we're going to have to check if p head, right, first. And then here we're going to say, right, so basically here we're going to say, well, p current, p next is not equal to m head or p head or whatever, right? And so this, well, yeah, I think, there we go. So I think we'll see out one of them first, and then we will, so now we can actually just do if p current is not equal to p head. So what this does is we see out the first one, right? So we output the p head data, and then we go to the next one, and we make sure that it's not the head again, right? So that's basically what I'm doing here. And then here, let's see, search. So so what do we do here for search? So if the p current is not equal to null pointer, so there is one possibility, right? One possibility where p current may be null pointer, and that is for an empty, right? So for an empty circular list, you'll end up with p current being null pointer. So we still have to check that. That's still a good thing to check. But then if the p current data is equal to the test, we return true. And p current is, you know, something like that, right? So if p current is equal to null pointer, then we don't do this. But if p current is not equal to null pointer, but p current dot next is null pointer, there's still one. Unfortunately, there's one case that we're going to miss, right? Because what if we have a single node? So this brings in an edge case where we have exactly one node, right? Where, and that's really the issue with these circular. So that's the issue with these circularly linked node lists, right? Because it's always possible that if you have just one node, then what happens? So this is really the worst edge case, is where you have basically can I make a circle? I want to make like an arc. Can I do that? I forget. There's a way to do it. Well, sort of, yeah. So I've made a Pac-Man, I guess. But basically here, if you have one node that links back onto itself, right? That's the problem. Is that so this is the real problem. This is a valid circularly linked list, right? So this is completely valid. But it's the most dangerous edge case for circular lists. And the reason why it's the most dangerous edge case is because the problem is that, like, the node exists, so that's good. But the problem is that the next node is itself. So if you ever go to the next node, you're just going to come right back to yourself, and back to yourself, and back to yourself, again and again and again. And so it's dangerous because if you don't do the correct testing, either you skip it, or you can end up in like an infinite loop. I guess it's a loop, so I don't even need parentheses on that or quotations on that. It is definitely an infinite loop. So that's the real thing about these circular link. Well, yeah. So if you do p next is equal to this, the problem is, remember what this is. This is a pointer to the circular linked class itself, right? Not the node that's inside of it. So that's why your original idea was the best idea. If p next is equal to m head or something like that, right? You want something like this. And so here we need to check if p head and p head data is equal to a test, then we return true. And actually, we can do this. We can do this up here before any of this stuff. So this tests the circular edge case, right? Or it at least tests the first element, so that when we then check to see, because here, if the first element had the correct answer, we want to return true before we check this. Because if the next element is the head, which in a circularly linked list it might be, then it might just jump past this and return false. But here it'll check it, so if it's the head, it'll return true, and then everything else, it'll just keep going. So I think that might actually be the way to do it, at least in this implementation. Yeah, so and then in the insert, it's similar. So when you're inserting at the end, you basically just do this while this is not equal to p head. But then here you have to actually do more like an insert like this. You have to remember, or you have to do more like this insertion, right? Where you're inserting, you're inserting in the middle at a position, right? Because everything is basically stuck in the middle of two nodes, even if that node is itself. So, yep. So I don't know if I'll release this code. This is kind of a bodge. I'm not sure. It's definitely not going to work. The linked list code works, but this code definitely doesn't work. Maybe I will give you guys this code and make it a little assignment to like fix it up so that it actually works, because it's close to working. It's very close to working, but it's not perfect, and there's a lot of but you know where all the problems are coming from. Like every single problem in this code, it comes almost entirely from this edge case here. So okay, and then the last thing I want to discuss is a doubly linked list. So here's what a doubly linked list is. And actually, maybe I'll just get rid of all these other nodes because I'm actually going to have to redo the arrows. Here's a doubly linked list. Let me try to get the arrow to point in the right direction. There we go. So what does a doubly linked list require in order to get this kind of structure, right? So if you have something like this, then it's going to require a certain type of, it's going to require an addition, right? We can't just do this with the regular linked list node that we've been playing with the whole time. Because you notice that there's actually, it's a double-sided arrow. And so what does a double-sided arrow mean in this case? Yeah, exactly. So, so in this case, we need two pointers, right? You need a pointer p next, and then you need a pointer p prev or m prev, whatever, right? So you need basically two. And the reason why you need these two pointers is because if you're going to go forward and back, then you're going to be able to, or you're going to need, what are you going to need? You're going to need something, right? You're going to need the ability to track both things. Now, the issue here is that the when you have this arrow, so, well, let's just copy paste. So basically, you're also going to have a prev arrow on the head, right? So on m head, you're going to have a previous arrow, and that's going to point to null, right? And then at the end, it's going to point to null. And so really, this is probably the most annoying one to implement, because instead of every time you do a pointer modification, basically the difference between this and the other structure is it basically doubles the number of pointer modifications that you need to do. Okay, so that's the issue with it, is that like every time you insert a node, yeah, that is the fundamental and next question. But so if you combine the two, there are, right, you can make a doubly circularly linked list. It definitely exists, right? it's basically like a table, right? So where you have singly linked, and then you can have doubly linked, and then you can have linear, and you can have circular. And so if your question is, do all of these exist? The answer is, right? Like this one would be a singly linked linear list, which is what we implemented. So definitely exists. Does a doubly linked list exist? Yes. Does a singly linked circular list exist? Yes. And does a doubly linked circular exist? Yes. They all exist. So do entirely linked lists exist, like each element stores? Maybe, but I wouldn't call them a linked list in that case. I would call that a graph. If you basically have linked lists that, I would call that a graph, because in that case, so you notice here that at most, the thing about a linked list, and that makes it a linked list and not just a more general data structure, is that basically any node is only connected to the previous node and the next node. Now, in a singly linked list, it's only actually connected to the next node. There's no way to go back, but basically, in the drawing at least, has the notion of a previous node and the next node. And so either you keep track of it with a doubly linked list or you don't. If you're keeping track of multiple nodes, more than just previous and next, then I would say that that is either a tree structure or a graph structure. So it could, so that's, and something like what you're saying is actually, what you're saying is a complete graph. Let me show you what a complete graph is. A complete graph is a data structure like this. Now, of course, this is actually just the mathematical version of it, but yeah, this does exist. So here are some complete graphs, right? Of, complete graph of 0, 1, 3, or not 3, 2, 3 nodes, 4 nodes, 5 nodes, 6 nodes, 7 nodes, 8 nodes, etc. So, so this is the data structure you're talking about, which is not a linked list. It's a lot more complicated than, well, it's moderately more complicated than a linked list. Okay. So, so let's discuss runtime. Okay. So, what kind of runtime does insert have? And we haven't really discussed big O, but basically, when I say big O of something, what I mean is essentially some constant times that number, or that function. Okay? And so, basically, when you insert into a linked list, right, at the end, so if there's n nodes in the linked list, then how many steps do we need to do to insert at the end? And this for just a circularly linked list, right? And so the answer, is going to be O of n, because we don't know how fast your computer is, exactly what implementation you're using. We don't know constants that relate to, say, how fast your processor is. Basically those two things, how fast your computer is and exactly what implementation you're using. But we do know that you have to step, yes, accessing an array location is O of 1, which is constant time, yes. So O of 1 means constant time. And basically you get constant time from, say, a RAM access. So you're right. If you know a location and you simply access it, then that's O of 1 time. But here we do know that we have to step all the way through n nodes to get to the end. Right? And so that's why we get O of n for insertion, at least insertion at the end. What about search, insert at position, and remove? So the thing is that all of these functions are basically the same, and the reason why is because they all do much the same operation. The only difference between them is what they do, right? Search returns true or false, insert finds the position and then inserts at that position, remove searches and then deletes this stuff. So deletion, like if we look at our code here, yeah, so you might say O of n, it depends, right? So in this case, there's a best and a worst case, and then there's the average case. So let's talk about all three. So the best case for search, insert at position, and remove is where basically either the position is equal to 0, right? So it's at the head, or really close to the head, right? So if it was at position 3, that would still be pretty good, right? Because that's only 3 steps, and we can pretend that 3 is a constant. So the best case of insertion is like an O of 1 operation. So the best case of search is where you search for the first element. The best case for remove is where you're removing the thing that you find at the first element. And inserting at position, the best case is where you're inserting at position 0, maybe 1, something like that. Very close to the head. So as long as you only go a finite, like a fixed, like constant number of steps, say like less than or equal to 10, then you can basically pretend that this is an O of 1 operation, right? So if your linked list was, say, 100,000 long, right, but you only had to 10 steps because you knew that you're going to insert, search, or delete from the first 10 things, then you could basically call that an O of 1 operation. On the other hand, so that's the best case. So what's the worst case? So the worst case is actually O of n, because same as before, right? Insertion at end, insertion, search, delete at end is the worst case, right? And it's the worst case because it means that you have to track through every element before you get to, you need to do whatever pointer operations, etc. Right? So basically, this will take n. When I say O of n, what I really mean is that the algorithm will take n steps. Right? That's what I mean. Is that whatever thing you're doing, it's going to take about n steps, and you can basically calculate that. So, for instance, on a linked list of, say, size 100, or let's say linked list of size 1,000, if you did like an insertion at end, or you did a search for something that wasn't in the linked list or something like that, let's say if you got a 5 millisecond runtime for this, right? So now, if I ask you, what's the worst time for a size 1 million linked list, right? And so this is kind of the way to understand runtime, right? So this is an experimental result, right? You ran it and you've got 5 milliseconds of runtime. So what do you know? You know that basically we're in an O of n world, and we know that basically the constant times 1,000, right, was equal to 5 milliseconds. So the worst case time for a 1 million size linked list would be that constant times 1 million, right? You would just replace the n. Now, what would that mean? So what that means is it's 1,000 times, right? It's 1,000 times as bad, so it's 1,000 times 5 milliseconds, which is 5 seconds, right? Now, I don't know if this is actually the runtime for for 1,000. This is just an example, and that's the reason you can actually kind of calculate your constant c a little bit. But the actual way people generally do it is you just take the new n divided by the old n times the old runtime. And what that'll do for you is it basically gets rid of the constant c, because you see that the old runtime was equal to c times this, and so you get c times the old runtime, or the old runtime was equal to c times old n. And then when you're dividing, you're multiplying by new n divided by old n, they'll cancel, but actually the piece of data that you really have access to is the runtime. So you usually just take the ratio between the new n and the old n, and you multiply it by the old runtime. And that'll get you, that's assuming, this is all assuming linear time, which means O of n operations. So we'll talk about things that, when we talk about sorting and searching, we'll talk about different runtimes. So the most common runtimes in programming are O of n, O of 1, O of n squared, and O of, say, n log n. So those are like the 4 most common runtimes that you'll usually see. And so basically, an O of n algorithm is not great, but it's much better than, for instance, an O of n squared algorithm, because, if this algorithm took 5 milliseconds, and we had an O of n squared algorithm that was actually controlling our runtime, then you would actually have to do new n divided by old n squared times old runtime. Well, so that's that. The good news is that those kind of questions, in terms of that, have to do with cache, right? So if you remember, or if you know anything about how processors work, load cache into their their processor, into their core memory, which is not RAM. It's like local RAM on the processor. So you're right that if you're accessing something in the same memory block, access 2 locations, and the first one is not in cache, and then the second one, then what happens is it gets loaded into cache, right? Gets that block loaded into cache, and then anything else that accesses inside of that block, any other accesses inside that block, will be faster. But here's the thing about that. In terms of algorithmic complexity, we generally ignore that stuff for O of n calculations. And the reason is because that all has to do with exactly like the internal mechanisms of any particular computer. And also it has to do with like the processor and how the cache works, and sometimes there will be cache read-aheads, for instance, that say like, oh, if you're going to branch and go to that memory location, we should preload it. So sometimes you'll actually get faster loads. Those are kind of hardware concerns that we're really not talking. And the reason why we don't talk about them is because there's so many different ways that it's implemented out there that we don't want to think about it too hard when we're thinking about the algorithm, right? But yes, you're right, that if you load from 2 different memory blocks, it's possible that it will affect the access time. But we generally assume, at least in this class, that all RAM accesses are the same cost, right? They all cost the same amount. It is always, so there in more advanced algorithmic design, you do actually take this stuff into account, where you'll say, you know, this algorithm is more likely to cause what are called cache misses, right? A cache miss is where you ask for a RAM location not already in cache, right? And sequential memory, yeah, I mean, it depends, right? I'm not 100% sure what you mean by that, but it depends on, yeah. So, oh, no, I kind of understand what you're asking, and the answer is yes. Yes. But yeah, a cache miss is where you ask for a RAM location that's not already in the cache, and that can take up to like 100 times as long as accessing pure RAM, right? So it's way faster if the computer can just ask. Yes, so most of when you do malloc or when you do new, generally what's happening is, even though technically you don't have any control over this, the operating system does try to allocate you memory in contiguous order. So if you ever output the location of pointers, you'll end up seeing that like one pointer is here, and then one pointer is like 8 bytes away, then the next pointer is 8 bytes away, then the next pointer is 8 bytes away. And the reason why it does that is because if it was just randomly selecting memory locations, it would be taking up memory space that potentially prevents large blocks from being allocated. And the other problem is that it would cause more cache misses, because it's possible that once it crosses a cache boundary randomly, then you'll have to load, like if you went and did your linked list thing and if the next object was in a different cache block, you would have to load that in from cache or from RAM. And hopefully the number of cache misses are relatively small when it comes to things. Otherwise, things do actually slow down quite a bit. Yeah, so, okay. Yep, basically that's that. So we'll talk more about this stuff later. I just wanted to kind of do it. So the average, let me just say before we go, let's talk about the average case. Right? So the average case is kind of a summation over all the different cases, right? And so the average case is where you'd say, well, it could happen at position 0, it could happen at position 1, it could happen at position 2, it could happen at position 3 or position 4, all the way up to position n. Yeah, you're kind of jumping to it. But as it turns out, this is, when you add up all the different positions like this, the average position is just n over 2, right? If you do this, and then you divide by, I guess actually this would be what? N minus 1. You divide by n, this will actually just be n divided by 2. Or either that or it's approximate. And so the average case, yes, in fact, goes to the center position, right? And so as it turns out, you call the average case is still O of n, right? Now, why don't we say O of n over 2? And the answer is because O absorbs constants. So O of n over 2 is the same as O of n. These are the same, basically runtimes. These are the same algorithmic complexities. Okay, so that's essentially where what we're doing. All right. So I think we've covered everything. We've done linked lists. So that's it for linked lists. We've talked about doubly linked lists. We've talked about circularly linked lists. Doubly linked, circularly linked. Next time we'll talk about stacks, queues, Deques, and then we might not even spend the whole class on it, and then we might start talking about sorting, searching, and more big O stuff. Okay? So that's for next time. So next time we're actually, so stacks, queues, and Deques are basically probably like the simplest data structures that you can come up with, but they're also the data structures that can use linked lists in kind of the most efficient way. You might be asking yourself, like, why don't I just use an array? And stacks, queues, and Deques do perform pretty well with linked lists. So, and for arrays, there would be extra cost if you had to like expand an array or contract an array or something like that. So, and we can talk about how vector does that in C++. So, okay. So yeah, sorting, maybe search, really sorting. Yeah, I'll keep search on there, but okay, cool. All right, I'll talk to you later. Dynamically allocated arrays. So those operate just the same as arrays. They are, to allocate them, the question is, when you allocate a dynamic array, do you have to visit every memory location to do that? And the answer is the operating system doesn't, which is why there's still junk data in there. If the operating system visited the entire dynamically allocated block, then it would probably set it to zeros or do some kind of safety thing for you. But it doesn't do that because it just knows that that block has not been allocated. So allocating a dynamic array can help, but it doesn't 100% fix the issue either, because once you reach the end of your dynamic array and you have to resize it, then that's an O of n operation. Whereas for stacks, queues, and Deques, everything is going to be a constant time operation. And I'll show you how we can always make linked lists give us constant time operations for these three data structures. So the general linked list issue, or the general linked list structure, has more than, it can produce bad runtimes, but not for these data structures. For these data structures, it's always O of 1 operations. Okay, I think that's it for now. I will talk to you all later.